if you add up all those fields, you would end up having zero field. So that's a non-curly field. That's a non-curly field as well. So what's the properties of a non-curly field? Is and a curly field. So let's say these fields which I have drawn here are field F. So for a curly field, if you imagine a path P, this is a path P, and then you take, so if you take a dot product with distance S along that path P, so I have this path, and what I do is I can define a certain ds element along this path at each point, and I can integrate this field with the ds. So if you see, you take a dot product of this field vector with ds, you get a certain positive number because both are in the same direction. Again, you have the field in the same direction as ds, you get again a positive number. You add up doing this, and overall you get a positive number, or in this case a positive number. So what if you do it for a closed path, it gives you a non-zero number. That's the property of a curly field. But if you do the same for this field, for example, let's say I have a path which is something like this. Again, the same kind of path. So I have ds in this direction, and I have ds in this direction, and I have ds in this direction along the path. So here the field is perpendicular, is parallel to it, so I get a certain positive number if I take a dot product of the field with the path element. But here, if I take a dot product, the directions are reversed. If you take a dot product, you get a negative value. If you add up doing all this, on this part you get a positive value, but on this part of the path, you get a negative value. And if you sum all of it up, what you get is that this integral is 0. So what we said about the field, the electric field, is that you can't have an electric field of this sort. Due to charges. If you put charges and you want to have an electric field like this, you can't have an electric field like this. And the reason is, if you take a dot product, if you take a path P, you take a dot product, so you start from here, take a dot product of E with a path for this closed path, so you start from here and you come back to the same point, you should get 0. If you don't get 0, you have a problem. Because what does this thing give you? So if you remember, we had a definition of scaling potential. This is minus E dot ds from A to B. But if you are taking a closed path, then you are basically doing an integral from A to A. So you start from a point A and you do it an integral to point A again. And so if you start from a point and you end up at the same point, we have seen it many times that the potential difference should be 0. If this potential difference is 0, it means that this E dot ds would be 0. And so this thing should be equal to 0 for electric field which is produced by charges. So that's the third law you have for electric field and magnetic field. So you have an electric field law for a closed surface, then you have magnetic field law for a closed surface, then you have an electric field law for a closed path, because this P is a closed. What if I do similar thing for a magnetic field? Yes. G. For electric field, which is formed due to charges, this has to be fulfilled. इसका मतलब है कि if you have charges, you can't have an electric field which curls around. But if you look at magnetic field are formed by those currents, and those magnetic field lines always curl around. They always form a closed circle. So if you take the similar integral for this thing, or a closed path, you get a non-zero value. And we have seen this, and this non-zero value is equal to mu naught divided by the current enclosed, and this is something which is called as Ampere's law. So if you have a current which let's say it is going like this, and you have a closed path, you choose a closed path around this conducting wire. So you can, and you start looking for the magnetic field. So if the current is in this direction, you would have magnetic field Ts. So these are the path elements, and if you look for the magnetic field lines, those magnetic field lines would be always parallel or anti-parallel to your integration direction. And if you have such a curly magnetic field, then what you get is a non-zero value of this integral, and this is given by mu naught by I enclosed. So if you take this path P and look at the cross section, what you would see that the current, this current which is coming out inside this path. So this current is enclosed by this path P, and that's why this integral doesn't give you a non-zero value. True? If you take another path, so you have this current I which is coming out, but if you take a path something like this, what would be this integral then around that path? It would be zero, because if you look at the magnetic field because of this thing, what you would have is a, let's say here you would have a magnetic field in this direction and a magnetic field in this direction, but here you would have a magnetic field again in that direction, there is smaller magnitude in that direction. So if you take a right hand rule, that's the direction of the current, the fingers give you the direction of the magnetic field. So here it would be counterclockwise, here it would be counterclockwise, but with a smaller magnitude. So if you take an integral of this sort, so along this path, so you start from here and you take an integral along this path. So if you are moving along the B, you would get positive values, but as you are moving, and this part you are moving against the B, you would get negative value, and if you sum all of this up, this integral would give you zero, because there is no charging. If there is no current enclosed, this integral will give you zero. So this is basically what we have done until now. You can summarize all of this in these four equations. So whenever you have charges, you have electric field. But you can't have charges of magnetic field, so the magnetic field doesn't have a single north pole or a single south pole. The electric field lines don't curve around. So the electric field lines which are formed due to charges, they are not curly fields, and they don't make complete circles. But magnetic field lines which are formed due to currents, they make complete circles, and that's why this integral is a non-zero value. So this is the crux of what we did until now. Any question in here? So, but whatever we have seen until now is something where we don't have any time dependence of the field. Like उस case में you don't have any time you are seeing in there. So there is no time dependence of the field whether in those two equations or no time dependence of the field in those two equations, which means that the electric field जो आपके पास establish हुआ है, that's a time independent, that is does not changing with time. Or the magnetic field due to the current, it is a constant magnetic field and it is not changing with time. So let's introduce time dependence into the field. So let's take a solenoid. And I introduce a current in the solenoid, I, and if I have this current, I would produce a magnetic field inside the solenoid. So what would be the direction of the magnetic field? It would be given by the right hand rule. So if you have a current flow, if you have the current flowing in this direction, you can say what the electric field direction is, magnetic. So the magnetic field lines you have magnetic field line like this produced inside a solenoid. What is the magnetic field outside? It's zero. So you have magnetic field here, zero. Magnetic field on that side equals to zero. So the only magnetic field you have in an infinite solenoid is inside a solenoid. What about electric field? Do we have electric fields in there? You do have electric field, लेकिन वो electric field कहाँ पे है आपके पास? They are inside the wires. They are inside the wire, and they are due to the current which is flowing inside. So you don't have any electric field outside. You don't have electric field here. You don't have electric field here. You don't have electric field inside. But the only electric field you have is inside the wire, which is making the current. Yes. That's a good question. So we said that if you have lines, let's say current क्यों produce होते हैं आपके पास? Because you have some charge gradient along the wire, and that's why you have a higher field here and a lower field here. So you have a certain field direction here, and because of that, inside the wire you have an electric field. So the question is, so you don't have those charges. So inside you have a metal, and outside you have a dielectric. So you do have a field outside, you do have a field inside, but outside you have a dielectric, you have air. So the air doesn't do any conduction. So basically there is no conduction there. But here you have, even if you have a very small field, you have conduction of electrons in there. So those fields are very weak. So whenever you have currents inside conductor, the field you establish due to those charges is very, very weak, because for metal you don't need high field, you need very low field. So the field produced outside USA, just a very small field, we basically ignore that for practical purposes. Okay, so what you have is magnetic field here, inside is non-zero, but outside it's zero. And you have magnetic field outside, and electric field also zero. The only electric field you have is inside the wire. What if I put a positive charge plus E here, close? that charge or that proton. If I put a positive charge here, what would happen to this positive charge? There is no electric field here, there is no magnetic field here, so nothing should happen to it. Even if it is moving, let's say, nothing should happen to it because there is no magnetic field here. So this charge won't experience any force as long as it is outside the infinite solenoid. Okay, let me do something else now. So I had a constant current which was flowing, so I had a magnetic field which was produced because of that. What if I change the current in time? What would happen to that magnetic field which is produced inside? It would change as well. If I increase the current which I am putting into the wire, if I increase the other magnetic field produced over here, that would increase in magnitude as well. True? So let's say if I have something like this, that I have a time axis and I have a current as a function of time. So as long as I have a constant current, let's say the current was constant, the magnetic field which was produced inside the solenoid, it was also of a constant magnitude. Let's say V naught. What if at a certain time T naught, I decide to increase the current? So if I linearly increase the current, that's what I do. So what I now have is a current which is a function of time. Until this point, the current was constant in time, but after this time, I have a current which increases with time. So what would happen to this magnitude of magnetic field inside the wire? It would increase, and it would increase linearly. Why it would increase linearly? Because what is the magnetic field inside a solenoid? This is given by mu naught and I, let's say the z direction is this direction. So that's the magnetic field inside a solenoid, where n is the number of curves, number of turns per unit length, mu naught is constant and I is current. So if you linearly increase current, the magnetic field magnitude will linearly increase as well. So that's what you see. Okay, so Faraday, who was a British scientist, he did this sort of experiment around 1830. And what he found out was that if you change the current inside a solenoid and you have a charge here, what does this charge would do? Let's say if this is stationary. The moment you try to increase the current, what would happen that this charge would start accelerating around the solenoid and start moving in a circle. So let me draw it in a better way. So if I look at this solenoid from this side, so what I see is something like this. So if I look at this side, I see that the current which is flowing in a counterclockwise direction. So you have a current which is like this. And what I did was I put a positive charge here. And you have a magnetic field which is inside the solenoid, and it is coming out. So you have a magnetic field which is only inside the solenoid and not outside the solenoid. If you increase the current, what would happen to this magnetic field? If you increase the current, this magnetic field would increase, but it would still stay inside. There is no magnetic field which is outside. But the moment you try to change this magnetic field or increase this magnetic field, this charge would start moving in a circle or start accelerating in a circle. What does this tell you? You do have a magnetic field here, but you don't have a magnetic field outside. So the magnetic field can't influence that electric charge. But what it tells you, that you have produced another electric field in this system just by changing a magnetic field, and the electric field is in such a way that it is making a curly field. If it won't making a curly field, the charge won't move around. Increasing a current inside the solenoid has changed this magnetic field, and that change in magnetic field has produced an electric field outside the solenoid. Yes. That's a good question. We said already that you can't have an electric field which is curly of this sort. But here it's completely opposite which is happening. Sorry? Because to start with, you had a stationary charge. If this was a magnetic field, you can't accelerate a stationary charge by a magnetic field. So it has to be an electric field, otherwise it won't make sense. So you produce an electric field which is completely opposite to what you were seeing there. So, which means that this is an electric field of a different nature. So you do have two types of electric fields which are there. One is called as Coulomb electric field, and the other sort is non-Coulombic electric fields. So Coulombic electric field are produces due to charges, but non-Coulombic field are produced due to changing magnetic fields. And this is a fundamentally new phenomenon which Faraday observed. For example, you can't derive this electric field from Coulomb's law. It's an independent phenomenon as compared to the Coulomb's law. So this field which produced here is a non-Coulombic field, so I would write it as a non-Coulombic field, a non-Coulombic field. That field which we saw there, which you see due to charges in a Gauss's law, all that field is a Coulombic field. So this is the field which forms around a closed path. What can you say about E? If I take the dot product along this path P of this non-Coulombic field around a closed path P, would it be equal to 0 or would it not be equal to 0? What we said there for the electric field, if you do it for the Coulomb electric field, what you get is a 0 value. But now you have an electric field which is curly, so you would get a non-zero value. Which means that you have to modify that formula which was there. So Faraday suggested that we can write E dot ds in this way, that we have E field which can be two sorts. It can be a Coulomb field, it can be a non-Coulombic field, and we have to take an integral of both fields to get the total line integral for an electric field. And if you do this, you can separate it into two parts. There is a Coulomb field dot ds or a closed path plus a non-Coulombic field dot ds. over a closed path, and this thing should give you a zero value because there's the normal electric field due to charges और जो charges की वजह से electric field produce होते हैं, they don't have any curl, and if they don't have any curl, this integral will give you a zero value, but this won't give you a zero value. So what would it give you? And the answer was given by Faraday again, and I give you just the answer, and I will explain it in a minute, but just I write it down. So that's the modified form of that of the law which we studied before, which is this one. I would explain all this term in a minute. So what I have written over there. So what it says that the line integral of this non-Coulombic force around a closed path is given by the time derivative of the magnetic flux multiplied by a minus sign, or it is equal to minus the total flux through a surface S and its time dependence. So I would explain what P should you take and what S does it mean here, and what is magnetic flux. We have already seen one equation concerning the magnetic flux, and that is this equation. So you have magnetic field dotted with an area, and they give you magnetic flux, and if you take a magnetic flux through a closed surface, this is equal to 0. But the magnetic flux which we are doing here is not through a closed surface, but rather it is through an open surface. So if let's say you have a magnetic field like this, and you have an area which is perpendicular to it, so you have a B field and you have an area which is perpendicular to it, so you can write its area vector is along the B field. What would be the magnetic flux in this case? The magnetic flux would be equals to the B magnitude multiplied by the area magnitude. So all the field lines are crossing, not all, but whatever facing the face are crossing through the surface. But if I have a surface which is lying somewhere like this, somewhat like this, parallel, it's like this, it's not a face. We have magnetic field lines. In this case, the surface is like this, but in that case, the surface is like this. So no magnetic field lines would pass through it. So what you have in this case is a magnetic flux equals to 0 because the area vector is perpendicular to the magnetic field. So what you can say, your magnetic flux head, that is a dot product of the area and the magnetic field line. This is the same way we define electric flux as well. The only difference was there was an electric field here and not a magnetic field. So, in a similar way, what I can do is, let's say if I have an area, but the magnetic total area is A, but I have magnetic field lines B passing through just a small part of the whole area. So what would be the total magnetic flux in this case? Then what I can do in this case is divide this total area into small unit areas so that I have area elements. And I take a dot product of magnetic field with each area element. And if I integrate it over this whole surface S, I call this surface S. It's not a closed surface, rather it's an open surface. It's not closing into a closed volume, it's an open surface. If I take this dot product, this gives you the total magnetic flux through this area. So if you have non-uniform magnetic field, then you have to take a dot product of a small area element and then you integrate over the whole surface and then you get the total magnetic flux. So let's come back to this thing. You have this solenoid with a current which is time dependent flowing through it, and you want to find this non-coulombic electric field lines around a certain path P. That's the path P around which you want to find the non-coulombic electric field. Yes. Okay. S normally I denote it for surface, and A is the magnitude of the area of this surface. Okay. So S or P, S I would use for a surface, and P I would use for a path. But path would have a length, and surface would have an area. So that's why I put an A there. So if you want to find the electric field line along this path, so you have to solve. Basically, you want to solve this part of the integral. There's the electric field, which is a non-coulombic electric field, along this path P, which is this path. Then what? So on the right-hand side, what you have is a magnetic flux here, which is this part, and this is magnetic flux through an open surface. And what is that open surface? In this case, is the surface enclosed by this path P. So this planar surface, which is enclosed by this path P, you have to take this flux through this open surface, so that would be your S. And where does lie the magnetic field lines? They are only inside the solenoid, and they are, so if I only so those are the magnetic field lines which are coming, or which are crossing this surface S. So if I look at up there, it's basically this surface. So the electromagnetic field lines which are crossing the surface S. So what does this right hand side say? That this, what would be this thing inside the bracket? It would be the total flux, total magnetic flux passing through this open surface S, and you have a time derivative of that. So what does it tell you? This whole thing, it tells you the time or the change in magnetic flux per unit time. And why there is a change in magnetic flux? Because you are changing current, and while you are changing current, you are changing magnetic field, and if you are changing magnetic field, the total flux is changing. Because let's say if you are increasing the magnetic field, the flux would increase. So what if I draw the flux here? let's say B is green. Okay. What if I draw flux here, which is phi m? What is the flux till time t naught? The magnetic field is constant by this time, so the magnetic flux through that surface is constant. So you have a constant magnitude of that flux. Let's say that flux is phi naught. But when you are increasing the magnetic field, that flux also linearly increases. So this, its time dependence would give you a constant value because this is a linear function. This flux, so this thing which is in the blue here, it is your d by dt of the magnetic flux, and the magnetic flux in this case, because the area is not changing, but the magnetic field is linearly changing, so the magnetic flux would linearly increase, and if it's linearly increased, this d by dt of magnetic flux would be some number, a constant number, which would be given by the slope of that line. That would be the slope of that line. Any question here? Yes. The potential energy associated with non-Coulombic. That's a very good question. I would come to that. So what we said, that the main difference between a Coulombic electric field and non-Coulombic electric field is that the Coulomb electric field is conservative field, but a non-Coulombic force is a non-conservative field. Because you are making a potential, you are coming back to it. So you can't define a potential in the case of a non-Coulombic field because it's a non-conservative field. Any field which is conservative, by conservative you mean that if you take f of any field with ds along a certain path, and if this is equals to 0, such a field is a conservative field. So this f is conservative. And if it is conservative, then you can define a potential for that field such that that potential is equal to minus df by dr in general. But if this is not equals to 0, then you can't define such a potential. So you can't define a potential for a non-conservative field. But what you can define is an EMF which is produced by such a field. I would come to that in a minute. Okay, then you have another thing which is a minus sign over here. And what does this minus sign mean? This minus sign, so what you have is, so what does it tell you? That if you have a change in the flux, it would produce a non-Coulombic field. So if you have a non-Coulombic field, if you have a charge, then that charge would experience a force, and that force would be given by that non-Coulombic field, of course, and not the normal field. So this F equals to QE. This is equally true for a Coulomb field as for a non-Coulomb field. So whether you have a field which is formed by charges, or whether you have a field which is formed by changing magnetic field, in either case, if you put a charge in that electric field, you would have motion of that charge because of the force which is exerted on it by that electric field. So this thing is equally valid for both a Coulomb field and a non-Coulombic field. ठीक है, force change नहीं होएगा. Okay, so because of that force, what this thing did, if I put a positive charge here, it started a motion. And this minus signs tell you what should be the direction of this motion. Whether it should be, for example, in this direction, or whether it would be in that direction. And let's discuss that thing for a minute. What should be the direction in this case? So the direction, so to find the direction of the motion or the direction of the electric field, so basically what you are finding is the direction of the electric field lines, which is E and C. Non-Coulombic field है, whether it is producing along in this direction or whether it is producing in that direction, that's what you want to find. And how do you find it? So you have to look at this thing. The direction, first you have to find the direction of dB by dt. What is the direction of dB by dt? So let's say if you have a magnetic field which is in this direction at time t. But this is a time dependent magnetic field. At a later time, this magnetic field becomes different and it has a longer amplitude. So the question is, how you come from here to here is by adding a certain vector to this original field, and then I would get that thing. So the direction of dB by dt would be the direction of this extra thing which I am adding into it. So what would be that direction? That would be a vector which of a certain magnitude in this direction. If I add this with this, I would get that thing. Or in other words, if the magnetic field in this direction is increasing, the change in the magnetic field is also in the same direction. But if you have something of this sort, that you have a d of t has that magnitude, but at a later time it has a smaller magnitude. So what I have to add into this magnetic field to make it smaller is to add a magnetic field of the opposite direction. So the dB in this case, the change in the d would be in the opposite direction in this case. So if the magnetic field is increasing in this direction, the dB is in the same direction, or the dB by dt is in the same direction. But if the magnetic field which is along in this direction is decreasing in magnitude, then it would have a dB by dt in the opposite direction. So you get the direction of dB by dt, which is that direction in that case, and this direction in that case. What would be the direction of minus dB by dt? As the opposite. So in this case, minus dB by dt would be, so dB by dt is in this direction, minus dB by dt would be in this direction. In this case, it would be other way around. True? So now coming to this point again, that what should be the direction of the non-Coulombic electric field? So you have to use a right hand rule, and the right hand rule tells you that you have to point your thumb along the direction of minus dB by dt. So let's come to this magnetic field which is in this direction. If the current is increasing, what is the direction of the increasing electric field, magnetic field? It will be in the same direction. So इस direction में जो magnetic field है वो increase हो रहा है. So what will be the direction of dB by dt? It would be in this direction. But what would be the direction of minus dB by dt? It would be into the pole. So what I have to do is, I put a thumb into the direction of minus dB by dt. So the fingers would curl along the direction of the non-Coulombic field. So what does it say? Is that your field is in that direction and not this direction. dB by dt, I already tell you कि अगर b increase होता है इसी direction में तो dB की direction भी उसी direction में. अगर वो decrease होता है तो dB जो है उल्टे direction में. But what you need इस integral के अंदर आपके पास dB b by dt है but with a minus sign. So basically you have to invert the direction of this. Okay? So if you have a field in this direction, अगर current increase कर रहा है तो ये field इस direction में increase कर रहा है, which means कि dB की direction दूसरी direction के अंदर है. So dB is in this direction, but what you want in that integral is a minus dB, so minus dB is in that direction. So the thumb goes into this direction, the fingers would give you the direction of the non-Coulomb wave. And that's how you find out what's the direction of the, there's something which is called Lenz's law. And you state it in different ways. For example, it can be stated in a way that if a current, so you have basically a motion, a charge motion which is produced, or a field which is produced by a changing magnetic field. So the field which produced would like to oppose its cause. And what is its cause? Its cause is an increasing magnetic field. What it would like to do is produce a magnetic field of a decreasing sort, so it decreases the magnetic field. And how it would decrease the magnetic field is by producing a magnetic field in the opposite direction. So the field इस direction में increase करना चाह रहा है, तो जो induced current है, it would try to induce a magnetic field in the opposite direction. So that's why this direction makes sense. So ये particle P जो है, it would move in this direction क्योंकि electric field दूसरी direction में, तो positive charge would move in the direction of the electric field. Any question here? So if this magnetic field was decreasing, you would have an electric field in the opposite direction. So, you're not asking questions, so yes? Yes? A negative charge. It's easier to see, you have to just look at E की direction क्या है. First this integral will give you the direction of E and C, okay, which is a non-Coulombic electric field. Once you get the electric field, the force is given by the charge. अगर charge positive है, तो force जो charge के ऊपर लगेगा, and C की direction में लगेगा. अगर charge negative है, force opposite direction में लगेगा. So it's given by that expression. Okay? So you don't confuse yourself by the charge by determining this. First determine the NC field direction. Once you determine that, then you can find कि force किस direction में लगेगी. अगर positive है, तो field के direction में लगेगी. Negative है, field के direction. So that's how you treat this problem. Okay, so you started with a steady current, then you increase the current. What if we decrease the current back to a steady current? What would happen to that B? So you would have B जो है आपका, it would go down again to the same value. What would happen to the EMF? Okay. Okay. So that's something I will use. Okay. So what is state? So you have this solenoid with a changing magnetic field inside, and I put a positive charge over there. What instead of a positive charge, I have a metal wire around it? What would happen to that thing? This is B field, which is a function of time, which means it's either increasing with time or decreasing with time. And instead of putting a positive charge over there, what I do is I surround it by a metal wire at a certain distance out. So as we said, let's say अगर B field increase कर रही है, what would be the direction of the NC field? This would be at each point like this. So this field, if you have a conductor around this solenoid, the field would be established inside the conductor. You can non-conservative field. And what would that non-conservative field does? It would produce a current because there is a field inside a metal. And whenever you have a field inside a metal, you do have a current. So what you would have is a current which would start flowing, and if I take the conventional current, the direction of the current would be the direction of the non-conservative electric field or non-Coulombic. So it's called non-Coulombic or non-conservative either is true. ये non-Coulombic field है वो non-conservative है. So NC stands for. So you would have a current which would flow in this direction whenever you have a conductor inside. So what you can say, current कब produce होता है within a circuit? Whenever you have a source which produces a current. So for example, if I take this thing, a simple circuit with an electromotive force source in it, which is an EMF source in it, and then EMF source is a battery. You produce a current in this thing. Last time we see a couple of examples of motional EMF. जिसमें हम क्या कर रहे थे? We were moving one bar, and there was a current producing of that motion, or we are rotating a certain coil and current was produced in there. And whenever you have a current produced, we say there should be some source of energy which would be causing that current, otherwise current can't flow by themselves. So where does that energy come from? It comes from an EMF source or for an electromotive source. So, first thing first, what is the electric field direction in this wire? It is, and where does this electric field comes from? Do they come from these charges? No. They come from the charges which are on the charge gradient on the surface of the wire. So here you have more positive charges, here you have less positive charges. That's how electric current is established in your typical circuitry. Because you have surface charges which have a certain gradient, which means that they change with distance, and they change with distance, that's the electric field they produce inside the wire, and then makes the current flow inside. What is the electric field direction inside here? It would be in this direction. What is the nature of these two fields? The field which is produced inside and the field which is produced here. Are they Coulombic or they are non-Coulombic? They are Coulombic because they are produced by charges. In this case, inside the battery, they are produced by the plate charges, and inside the wire, they are produced by the surface charges. And in both cases, you have charges, and if you have charges, you have Coulombic field. And if you take an integral of this Coulomb, of this electric field, whether this one or whether that one, so you start from here, you take a path along this, and you take a path P over the closed surface, and what you would get is a zero. So you have a field. So let's say if you move from here, what you would have is ds is in the same direction. ds as E field, so you would add up, but here you have a strong field, and in this case ds is in this direction, which is opposite to the electric field. So you add up the electric field and you subtract it, you get zero again. So no matter you take stationary charges or you take currents which are formed by charges, इलेक्ट्रिक फील्ड चार्जेस की वजह से होएगा, चाहे सर्किट के अंदर हो चाहे चार्जेस की वजह से हो, you would always have E dot ds equals to 0. But okay, so there was a current which was flowing in this, and the direction of the current was along the electric field. And we said that current induced कहाँ पे होता है? Because of a work done by the battery. So what we assumed was, so you have an electric field here. What if I put a negative charge on here? क्या होएगा उसको? A negative charge, so if you have current flowing in this direction in the circuit, it means that the electric charge will flow in the opposite direction, so in this direction. So if I put an electric field here, where would this electron go? It would try to go in that direction, which is opposite to what the current flow is. So to maintain the current, you have to apply a certain force on it and a certain external force. And how do we say where it is applied? Is we assume that there is a certain kind of a motor inside which moves those, which applied a certain force on this on those electrons opposite to the electric field lines. So the electric field would have a force in this direction, which would be the Coulomb force. So इस प्लेट की वजह से इलेक्ट्रिक फील्ड इस डायरेक्शन में होता है. So if you have an electron there, the electron would have a force in the opposite direction. So that's the force which is a Coulomb force. But then you have a force which is due to the battery, and that force is a mechanical force, and it should be in the opposite direction. So you have a force which is due to the battery, which I call as F battery, for example. This F battery is a non-Coulombic force. Why it's a non-Coulombic force? Because it's not due to charges, it's due to some belt which is moving the charges, and not due to an electric field which is produced by charges. So you have a non-Coulombic force which produces that current. And we said whenever you have non-Coulombic force in your circuit, that sustains the current. अगर ये बैटरी ना हो, you can't sustain the current, it will die out because of this electric field. Is it getting too much? So actually at the end of electromagnetic, this course is something in which you build up on many small things, you develop all those concepts, and at the end of it, you have to somehow combine all of them, and that's the beauty of this course. And at the end you see the whole picture. Okay, how does the whole thing works out? Okay, so if you have such a thing, we define an EMF of a battery. An EMF of a battery, क्या था आपके पास? The EMF of the battery is the work done on the charge per unit charge. And that work done is the work done which the battery does on the charge. And what is that battery does? It applied a force which is a non-Coulombic force. So that is a non-Coulombic force multiplied by a distance s. Because if I take this whole distance as L, S, so this electron is moved from this point to that point by the battery. So the battery is applying a force from this point to that point. So what is the work done by the battery? Is a force multiplied by the distance. Because it's done by the battery and it's not done by the charge. If I leave the electron there, what it would do? It would go to the positive. वो वर्क जब आप कैलकुलेट करोगे, it would be by the Coulombic field, but it won't produce a current. Okay? So if you have to produce a current in the circuit, you have to apply a non-Coulombic force or force to the circuit. Okay? So you have this thing divided by E. Let's say if I divide this total path from this plate A to this plate B into small distance element ds and find the total work done. So वो क्या होएगा? That would be equal to F non-coulombic dot ds, which is the small from A to B or from the positive plate to the negative plate divided by E. That's how an EMF is defined. And if I write as Fnc, which is a non-coulombic force, dot ds from A to B, I can rewrite this at this. So E has to मैं F integral के अंदर लेके गया. So you have a force on a certain charge divided by a charge. What is that thing? That is an electric field. So E जो है, that is an electric field, but in this case it's not the normal electric field, but rather it's a non-coulombic electric field. So that's a non-coulombic electric field. So the definition is कि जो आपके पास F and C है, this is equal to E into the. That's how we define the non-coulombic electric field. So that's a non-coulombic electric field dotted with ds from A to B, where A is the positive terminal of the battery and B is the negative terminal. So that's how an EMF is defined. We already had defined it, but I have made it into an integral form just to make things a bit more. Okay, so coming back to this circuit, what you have is आपने magnetic field change करा है, and because of this magnetic field you have current will start flowing around this circuit. It means that some sort of forces start acting on it. और वो force आपके पास क्या है? There's a non-coulombic force, and that non-coulombic force initiated a current. So you have an EMF around that circuit. And what would be that EMF around that circuit? In that case, what I have to do is I have to take, instead of from A to B, I have to take a closed circuit. It's not just a battery, it's a full loop around which the whole force is acting. So the non-coulombic force, it acts along the whole loop and not just in a small segment of wire. So I have to take E and C dot ds. That would give you the EMF around such a wire. True? और ये non-coulombic electric field आई कहाँ से है? From changing magnetic field. What is this thing then? You look at that, that's the EMF. So that completes this law, which is called as Faraday's law. And whenever you have a changing magnetic flux, it produces a non-conservative electric field, such that that non-conservative electric field can act as an EMF source, and that EMF is given by that field. Next time you would have a look at this in detail and do a few examples. Okay, how to calculate, for example, this non-conservative field. Once you calculate it, how to calculate the EMF and all the different properties. Any questions here? A bit too much, but we would do a few examples and this would become clearer and clearer, and you would see. But the important message is that this is a fundamentally new field. It's not the same field as you encounter in a Coulomb's law. It's not that. It's a completely different field. It's called a non-Coulombic electric field, sometimes also called a Faraday electric field, and its nature is completely different from Coulomb electric field. Both have fundamentally different characters. Okay, so yeah, any question? अगर हाँ, that's a good question. तो अगर आपने, let's say, you have to take this electric field with a constant velocity from here to here, फिर आपकी जो बैटरी की फोर्स है, जो नॉन कूलोम्बिक फोर्स है, इट हैज टू बी ऑलमोस्ट इक्वल टू द कूलोम्बिक फोर्स। तो क्या आ जाएगा? तो CMF जनरेट हो जाएगा। It is slightly higher than this, like exactly, otherwise it would not move at all अगर आप चार्ज होती है, but nevertheless it's almost equal. Okay, yeah.